In this lecture, I will discuss the transverse vibration of laminated plates. Specifically, I will be considering the spatially orthotropic laminates. And for those kind of laminates, the transverse vibration of the plate is governed by this equation, which is highlighted here. And this equation is obtained from the more general equation which I have already shown in my first handouts, and that is the equation 9. And this has the elastic constants dij as well as bij, and then in the right side you have qn, where is the q is for the transverse load, and this capital N is the nonlinear term which relates the in-plane forces and xx and yy and nxy, and I0, I1 and I2 are the inertia terms. And after that, if we simplify for the case of symmetric laminates, we have seen that this Bij terms goes to 0. Along with that, this I1 also will become 0, which is mentioned here for symmetric laminates. And that actually simplifies this equation as this. And after that, if we further consider the spatially orthotropic laminates, which are such laminates for which this Bij will be 0, along with that there won't be no bending and twisting coupling, which means D16 and D26 also will become 0. And example for this kind of laminates are symmetric cross-ply laminates. And for those kind of laminates, we see that the bending behavior of the plate, which is governing the transverse deflection of the plate, is reducing to this form. And from this, again, for the transverse vibration of the plate without any forcing function involved, that is the natural vibration. For that natural vibration, this q terms will be 0. There will be no transverse load, and the n also will be 0 because there won't be any in-plane forces. So then we will have 1, 2, 3, and 4 and 5. So these 5 terms will be there in the governing differential equation for the transverse natural vibration of spatially orthotropic plates, which is written here. Here I0 and I2 are the inertia terms, and it can be denoted using this summation rules for laminated plates. And in integration form, we know that I0 is rho z dz and I2 is rho z square dz. I0 is rho dz, and I2 is rho z square dz integrated over the thickness. And when we see that the density of a particular lamina is rho k, then I0 and I2 can be expressed in a summation form like this. And here L is the total number of layers in the laminate. And now we'll discuss how we can solve this governing differential equation for two kinds of plates, or rather two kinds of plate boundary conditions. The first one will take the simply supported plates, and for which we have Navier method. And the second bounding condition will be two opposite sets simply supported, and other two edges will be either free, clamped, or simply supported. So that kind of plate bounding conditions will be solved using Levy method. So both Navier and Levy method will be discussed here. First, we will discuss the Navier method. And in Navier method, the uh, transverse uh, deflection of the plate is assumed to be periodic, and that is expressed using this equation. Uh, Earlier, we have seen that for plate bending, we have used a deflection, the transverse deflection, as a Fourier sine series, uh, double sine series, where it is expressed at Wmn sine alpha x sine beta y, where alpha is m pi by a and beta is n pi divided by b. And in addition to that boundary condition, here we see that this W, capital Wn, Mn, is actually a function of time, and that Wmnt is expressed as some Wmn times e to the power I omega t. And this is the periodic term. And then altogether we can say that this is the uh, transverse deflection, which is described in double Fourier sine series. And here this omega is the natural frequency of the plate. So here just make a note that this is omega, and whereas this is actually the deflection W, which is now a function of x, y, and time t. Now if we substitute this W in the governing differential equation, then we get this equation. So it is very easy to see how this form of the equation is coming. And now we see that for this equation will be holding for every point x and y of the domain, and therefore this expression, which is written in here, this expression will be valid such that the bracketed term here will be, sorry, there is one bracket missing here, that's why. So the for holding this equation for each point x and y, so the term within that second bracket or the braces should be 0, and from there you can get what is the expression of the natural frequency omega. So if we get this equation, then here you can solve for omega, and omega will be omega m n square. So this is for this omega will be depending on the m and n we choose, and this can be expressed in this form. And here I0 bar is considered as a new variable, which is dependent on I0 and I2 in this way. So this is also dependent on m and n. So for different values of m and n, we get one unique frequency omega n, and for that particular m and n, we get also one mode safe, which is a function of x and y, which is nothing but the reflected safe of the plate for that particular frequency omega n. So here this Wmn is the magnitude or amplitude of the vibration for that particular mode m and n. So m and n1 means we have one sine wave in the x direction and another sine wave in the y direction, and that will be called as omega 11. And most of the cases we generally see that omega 11 is the lowest frequency or the fundamental frequency, but it is not necessarily be the omega 11. It can be any other modes which will be the lowest frequency, but as we see that for most of the cases it turns out to be the omega 11 is the lowest one. We'll see how the mode safes will look like for different m and n when we will go through a MATLAB demonstration. And now we can also make a note about this, that when the rotary inertia is not zero, so I2 not zero, then it is not very simple to find the lowest natural frequency. And the reason is this: you can see when I2 is not zero, then m and n will be both in the numerator and also in the denominator. And it's difficult to see which m and n will give you the minimum omega, but you have to calculate for different m and n and see which one is your lowest frequency. But as it happens, if I don't consider I2, then generally after looking this equation, so when I2 is 0, you can see the denominator term will be independent of m and n. So m and n will be in the numerator, and probably it will be easy to see for which m and n we get the lowest frequency. All right, so now we'll see for particular few cases how this omega expressions are coming out. So for cases with no rotary inertia, when the rotary inertia is actually neglected, we can see the omega mn square will be expressed in this way, already discussed earlier. And then here for square plate, b by a will be 1. So then further this is the simplified form of the omega and mn square. And then from here you can see the fundamental frequency will be when m and n is equal to 1, and that is the expression of the fundamental frequency omega 11 square. And then okay, this is for the specially orthotropic plate, rather square plate without the rotary inertia. We can see how the fundamental frequency expressions are coming. And then if we further simplify the plate to be a homogeneous isotropic plate, then we can see that this bending stiffnesses will be related to one single stiffness D, which is EH cubed by 12 into 1 minus nu square, and we'll get a very simplified form of the frequency omega mn, and you can see for a uh, for the fundamental frequency mn n will be 1, and that omega 1 is this, and for square plate again this will be by will be 1, so it will become 2, so it is 2 pi square by b square root d by I0. So that's your for isotropic plate square plate, the fundamental frequency will come out like that. But for rectangular plates, this b by a will be not equal to 1, and we will get frequency which is dependent on the plate aspect ratio. Okay, now we'll see some typical results for some material properties and plate aspect ratios. So here the material properties are taken as this. The E1 is 10 times E2, and then Z1 to 0.5 times E2, and E2 is 0.25. Then the non-dimensional frequency omega mn are shown, and this is for a square plate. So this is just to get some non-dimensional frequency, so that it is easy to compare. And this is your dimensional frequency omega n, and then you make it non-dimensional by multiplying this omega n by b square by pi square, b square divided by pi square times root over rho h divided by d22. And we have shown here, and this table you can get in Jane Reddy book. And here one laminate, single lamina is taken which is 0 degree, and another laminate is taken as 090 symmetric, so 4 layers, and the frequencies are reported, non-dimensional frequencies are reported here. And you can see in this m and n are written. So first is m and n11, it is the fundamental frequency. The fundamental frequency means this is the lowest frequency, so you can see this frequency is the lowest. So for this symmetric laminate 2.519, for 0 degree it is 3.6, and then the other frequencies are reported, and the corresponding mn and also shown here. So here this table is actually first sorted using this frequencies, 0 degree laminate. So you can see this increasing frequencies are reported, and then corresponding mn and n are written here. But to report the same the frequency results for 090 degree in the same table, there is some actually the frequencies are for these two cases reported in a different way. It should have been, this one should have been the third one, which is 8.515, and the third one should have been fourth. The only difference, because this actually if we rank the frequency for this case, this would be your first frequency, and 4.98 would be your second frequency, and 8.515 will be your third frequency, and 9.78 will be your fourth, and then 10 is your fifth. So here it is shown to just report in the same table in this way, because if we take 2 1, that is M2 and N1 actually gives you the third frequency for this laminate 090, whereas the fourth frequency for 0 degree. And 1 3 mode M1 and 3 N3, that gives actually the third frequency in this case 0 degree, whereas the fourth frequency in this case. So that you can make a note of it, but uh, if we understand this table how it is, then this reporting is not a problem. Okay, so this is how it was reported in JNRD book, and I just mark this two frequencies to just explain this things to you. All right, now if we include rotating inertia, you can see that for this particular material properties, there is not much change for aspect ratio 1 and 2, but for the aspect ratio 0.5, we can see the frequency is slightly lower when we take rotating inertia. So you can see 8.515, it is 8.513. It's very like negligibly lower, you can say. Now I will try to show you how this calculation can be seen in a MATLAB code. Let me just explain this MATLAB code a little bit. So here first let us say I want to calculate frequency for M and N1, and then square plate, so A and B same, so just I have taken 4 as the plate length and width, and H is A by AT taken here, S is the aspect ratio B by A, and then the D matrix is calculated from the material properties. Here you can see this is the material properties taken. E1 is 10 times E2, where E2 is taken 1, and then G12 and mu12, and this is the laminate sequence, the symmetric one, and then for that we get D matrix, D11, D2, etc. So this is what it is taken from this output. That is the sub function I showed. The sub function is written below the main function. All right, and you can, I have shared with you this code. You can have a look on that. Then rho is just taken some arbitrary number, because when it will be non-dimensionalized, these numbers will not make any difference. So you can change and see that your frequencies are coming same. And then alpha, beta defined as it is, m pi by a and m pi by b respectively, and then I bar and omega mn. So that's the direct formula we have put. And then this is the normalization. So b square divided by square times square root of rho h divided by d2, 2. Okay. And then this is for the mode shape. So once frequency is obtained, now we'll see how the mode shape will be looking for that particular mode. So now if I run for first mode, I get 2.5193, and if we refer this, yeah, I have already highlighted 2.519, we report it here, and you can see the mode shape. So it is one wave here, one sine wave, another sine wave. Okay, and this is sometimes we call half sine wave, because it's the positive side of the sine wave, one half sine wave. So one half sine wave in both the direction x and y. So this is your first mode, and then if we change m, so you can see here what is your next one, 4.986, which is m1 and n2. So I can just change this to m1 n2 and 4.9859, which is written here, and the mode safe you can see. So n2 means along y you have two half sine waves, so that means one full sine wave, and along x you have one half sine wave, like this. So that is your mode safe for m1 and 2. Like that you can change and see you are getting this values. And for the second table you can also check like e1 e2 that ratio 10. If I just make a by b 0.5, you will get this number. So that can be also seen here. So here b is higher, a is low, so a2 b 4.5. So if I run, I'm getting 10.077, and what is that? Let me check again what happened. So if I just make it 2. So without rotary inertia, I have made u1 e2 10, a by b 0.5, a by b 0.5. Okay, so this is your fundamental frequency is only reported. So I have to make this is 1 So you can see here, so I made that mistake. So it is the fundamental frequency omega 1 so let me run again to see what is happening. 8.5150, and you get this number 8.515. Okay, so this is your first frequency. You can see this this is the mode set for that particular plate. Okay, now let me quickly show you how the other bounding condition which is done using Levy method. We can quickly go through this. So again, you can refer to the bending case, bending of laminated plates, and then for the vibration, we will also proceed with similar manner. So one direction, the sine series will be Fourier sine series will be assumed, and and with that we will get a ordinary differential equation. So that's the approach in Levy method we adopt. So here you can see the periodic for periodic motion we use the deflection as this omega bar xy times e to the power I omega t, where sorry, this is w and this is omega. I make sometimes a mistake in saying this thing. So this is your, and also maybe my handwriting also not very nice to distinguish these two. So this omega is the frequency and this w is your deflection. W bar xy is nothing but w capital Wn x times sin beta y. This is already we have seen. Okay, and this we know that this bounding condition will automatically satisfy the simply supported bounding condition y at y is equal to 0 and b. So the simplified boundary condition is nothing but the displacement 0 at that edges, and the moment is 0. So the moment, there is no constraint about the rotation, so that's why there won't be any moment. All right, so if we put this in this two equations, you will see they satisfy this boundary condition at edges y is equal to 0 and y is equal to b. All right, so here we can see this edges will be simply supported. So y is equal to 0 and y is equal to b. Whereas this x is equal to 0 edge and x is equal to a, those two edges will be any boundary condition among this free, clamped and simply supported. Okay. All right, so now if we put that assumed solution in the governing differential equation, and here the governing differential equation will remain same as it was in Navier method. So then the linear differential equation, sorry, ordinary, yeah, and linear also. So ordinary differential equation, we get this, and that we can rewrite again in a simplified form as this, where p is just d11 and q is written in this way, which is I2 dependent, and r is also written here, where I0 and I2 both will be there. And for this differential equation, the general solution will be written in this form. And here this lambda and mu will be calculated as this. So here PQR will be there, where the PQ and R is defined in this way. So if we know PQR, then we can calculate lambda and mu. But here you can make a note that PQR, if not P, but Q and R is actually omega dependent. So there is some frequency term within Q and R. So this lambda and omega has frequency terms inside. And now we can actually apply the boundary conditions, and then we'll get four, like we'll from the boundary conditions we'll get four equations for these four constants C1, C2, C3 and C4, and that four equations, considering that four equation, we will actually get an eigenvalue problem, because the determinant of to get non-trivial solution, the determinant will be 0, and that determinant will lead to a characteristic equation, and that characteristic equation will have the frequency omega, and solving that omega will get frequency, and after frequency we can solve for these constants to get the mode safe. Okay, so this is your Levy method, and I've not shown you for a particular boundary condition how the analytical expressions are and the expressions will be there for different cases, because they are actually lengthy. What I have done is I have given you a MATLAB code where you can just put those boundary conditions, and quickly you can get answer for those frequencies. But you can refer any book where you will get the analytical expressions, like Jane Reddy and maybe some other books also. So the results for one typical cases is reported in this handouts. Here the material properties are taken like this, then the non-dimensional frequencies are reported in this way. Omega is dimensional here, omega bar is non-dimensional, which is just omega the dimensional frequency multiplied by a square divided by h times square root of rho divided by a2. And for a square plate with laminate sequence as this, the frequencies are reported for 6 boundary conditions in this table and 3 modes. And we already know that for Levy type plates we get 6 boundary conditions. Two other edges will be always simply supported, and others will be either simply supported and simply supported clamp, clamped, free simply supported, and free clamp. So for these cases, these are the reported values. These are 3 modes, the non-dimensional frequencies. Now we'll see how we can get these numbers. I have done for 2 cases, simply supported and clamp, but you can just modify a little bit in this code, and you can obtain the other 4 cases also. So let me go to that Levy solution case. So let us say I'm taking this clamped one, and first let me explain this, and then I will go to the next one. Okay, maybe I can first take simply support. I don't know whether clamped I have changed it finally, but okay, let us run and see. First, let us run simply supported one, because I know, like, I'm very sure that it will give you the same number, because I have just verified before making this tutorial. Okay, so here we have only n here, so that n is taken 1, then a and square plate, so b is equal to a, then e2 is 1, but anyway you can put some other number, but you cannot put other number here, because in this code what I have taken is I have taken material properties in this way, so that e2 is already taken 1. So if I have to change e2, then you have to put also change the material properties accordingly. So e2 is 1, and then row some number 20, and I0 is row h, I2 0 for time being, but you can put the actual I2 to get the rotating inertia terms included. And then in this word, because this you have to solve the characteristic equations to get its roots, and we know that these characteristic equations will have the sines, cosines, and sine hyperbolic and cosine hyperbolic, and that will lead to some transcendental equation, so which will have many roots, and normal the solve command will not work. So what I have done here, I have used a Newton-Raphson method. For that you have to just give an initial guess value, and then around that value it will find the root, and it will give that corresponding frequency. So we'll actually give the guess value of the omega bar, which is included here, and then it will find the actual omega bar, which is solving that equation, or which is satisfying that characteristic equation. So once omega bar is taken as input for this function, then from omega bar I am going to find omega, which is the dimensional frequency, because in formulas the dimensional frequencies are there. So that's is done using this command, and then all the stiffness matrices, and then I am using symbolic commands for x, y, and abcd. Beta is given, then pq are defined, then lambda and nu defined, and then omega, sorry, w, capital W is defined, And then for the simply supported bounding condition, we know that the W is 0 and dW by dxx will be 0. You just see by applying the boundary condition, you'll see that that mxx, sorry, myy for this case, myy has to be 0 at x is equal to a, and then myy is equal to 0 will lead to this equation. And then if we put these boundary conditions, like these two things will be 0 at both x is equal to 0 and a. So 0 first 2 and a second 2. So you will get 4 equations. And then you arrange them in a matrix. And then the determinant of that matrix will be 0. And so that's what we get. And then f. So from this equation, my output is f, and the Newton-Raphson method will look for where this f is 0. And this Newton-Raphson method is written compactly, so it's a standard routine. You can get a similar routine maybe from internet, but you can make on your own. This is actually my own routine, and then you just use run command, and you can see I give a guess value for this particular case 18, because if you see here, yeah, it's close to 18. So at one point you can see like how to guess these values, but we'll start with some arbitrary number, and then we'll see for some cases it may take a long time, and maybe it will not give you real root, so then you can change, and you can see after some values it will start giving you some real solution. Okay, so for this case, if I run, you can see, because this is doing some iteration, and then after few iteration it has given you 18.89123, so it is this one. And then for modes number 2, I have to put this to 2. So here I'll go, and then I'll put n is equal to 2. Then even I can start with this 18, but you will see it will give some different number. So when the guess value is little far, it takes time. So that's the issue. So you can see the actual value will be around 26.93. So it's taking time. Maybe it will be lost, or I don't know. Let us wait for a while. Otherwise, I'll kill this, and then I'll give a value which is near about that number. Okay, I'm running out of my patience. It's not giving. Come on, give some number. Maybe it will. Okay, let me kill. I have waited enough because I'm making a Control C. Alright, so I've done Control C. Now I will give 24 or something, and you'll see. Maybe it will give you the number quickly. Yeah, so 26.937. It's 26.938, but I think I have 74. Alright, so it's pretty close to that. Maybe there is. So 75, then you now round off that, then you will get 78. Sorry, 938. Alright. All right, now let me see this Levy solution CC, which is the clamped one, and I think this global code may not be needed. So let me just, because we need this, don't need global here, and then the difference is here, instead of the dwd xx, we have to just make dwdx. The slope will be 0, the deflection and the slope, and then nothing changes, everything same. Okay, and then all right, so after that, in Newton is same, only run. You have to change this file to cc, and let me check the value 40.74. So you can give some close number to get quick answer. So let us say 39 or something. I'll give, and 40.743, 40.743. So yeah, so you can see, you can get the frequencies. After frequencies, you can calculate the mode shapes by solving for A, B, C, D, the constants. But that I think you can do it on your own. So with this, I will end this lecture here. And what I will suggest, you modify this code which I have given for other boundary condition, and try to reproduce those numbers. With that, let me end here. See you in my next lecture.